There's like a normal, there's a normal sports one and there's the overflow. Overflow is really, well, no, there's not. He gets frustrated.
Yeah. Oh, you're very welcome. They do need coaching. Yeah.
11. Ooh. Missing a few people.
Dropping like flies.
It was a tough night tonight.
You have seen them? Yeah. I've seen her in person. I hope.
I noticed that I now enjoy all the things that I used to see as a punishment when I was little. I have to go to bed early. I don't have to meet people and I can't go to the party. Good morning. So where's everybody? Yeah, we make a start. I'm pretty sure somebody will turn up or not. They're trying to find parking. It's not even term time. We can give it another 5 minutes, if that's all right. Yeah. Okay, let's start gently. Okay, that's probably is a good approach. So, most wonderful good morning, everybody. It is day 3 in the Big Brother house. No, sorry. You're probably. Do you remember Big Brother? Yes. Is it still going? Really? Good Lord. I thought by now this is okay. Good. Good morning, day 3 in the Big Brother house. What I want to do with you today is basically carry on from where we left off yesterday with this student t-test, because inevitably you will perform some kind of t-tests for your analysis, since this is, my understanding, is the most common tests when you are dealing with continuous data. And I gave you a list of the sort of requirements for the classical t-test yesterday. I will come back to that. And what I'm going to show you, at least in this first part of this session today, is basically how we, in a way, get this p-value. Because we said the p-value is really our decision-making tool that we use to say, yes, we believe the null hypothesis is valid, or no, we reject the null hypothesis. And that gives us then this decision tool where we say, for example, if we compare a drug with a placebo, yes, the drug has an effect, or forget the drug, just give it to the rabbits. It does not have any effect. It doesn't do anything, right? And that is basically what you are really interested in. Does it work or not? So I told you these conditions, terms and conditions, under which the classical t-test is valid. And I told you it has to be continuous data. You should never use a t-test on discrete data. And the reason for that is because this t-distribution is a sort of a continuous distribution, like the normal distribution. In fact, the t-distribution or the t-test relies on the fact that the populations that we are sort of estimating are more or less normal distributed. I told you what makes a normal distribution. It is this bell-shaped curve, it is symmetrical, and it has these particular characteristics that, for example, 95% of all the data are within the span of two standard deviations to the right and two standard deviations to the left. It's an absolutely defining character of a normal distribution. And a lot of processes in nature are normal distributed. That's actually where it got this distribution got the name from, because it's normal that it's normal distributed. And if you see any other distributions, then people tend to say, oh, that's a little bit weird. They're not called weird distributions, but it's abnormal, that's the word, if it's not normal. We said the samples must be independent, and I will this morning show you exactly what this means. Basically, it means that the two groups that we want to compare with each other, with drug, without drug, are totally independent measured. So the measurements in one category, say placebo, does have no effect on the measurements in the treatment arm. Yeah, and that's absolutely crucial for this t-test that we are going to do. The classic t-test makes the assumption that the variability, the standard deviation of the two populations are the same. And of course, that is a big ask because we really don't know what the standard deviation, what the variabilities of the populations are. We have very little information, so we really have to guesstimate. Good morning, good morning, good morning. So we really have to guesstimate what our standard deviations might be. But there are ways we can do that. And The classic t-test also says we need to have, both samples need to have the same number of observations. So if you test, for example, 20 participants in the placebo group, you need to have 20 participants in the treatment arm. Because otherwise the t-test will give you some numbers that may or may not be absolutely correct. So these are the terms and conditions under which you can do a t-test. And we looked a little bit at, I gave you some p-values and you had to make a decision. Bless you. Is there, what do we do with the null hypothesis? And we said if p is lower than our alpha, h naught must go, so we can reject the null hypothesis. If the p-value is higher, then we cannot reject the null hypothesis. We fail to reject the null hypothesis. We can't say we accept the null hypothesis because we can't accept a null hypothesis. We can never prove a hypothesis. We can only disprove it. And that's very important. And I thought what we are going to do in this first part is I sort of give you a little bit of the mechanics, how we actually can calculate this p-value so that you can do that potentially for any assessments also. Again, I will show you how you can use an online calculator, or this online calculator that I showed you and that I've given you the link. I hope you've got it bookmarked, because this online calculator will be your lifesaver for your assignment. Just so that you know. So let's just simply work with an example. Here are our drugs, our treatment, and we have the placebo. We measure tumor size, for example, without drug, and here the treatment. And you can already see that there is a slight deviation from what I mentioned earlier in terms of when the t-test is valid, because what you can see is that it does not have the same number of observations. So one needs to be a little bit careful, but I'll show you then in a minute how we can overcome that problem. So these are the data, and before you become totally trigger happy and say, hey, cool, now let's do something, let's do weird and wonderful calculations. The first thing that you need to do, and that's absolutely essential, is that you follow the protocol or you devise the protocol and say, first thing that I need to do is I need to write down what my protocol, what my steps are. And here is the protocol again. We have to formulate a null and an alternative hypothesis. For the null hypothesis, we can say there is no difference between the two population means. Sorry if I have to harp on about that. We cannot compare the sample means because the sample means could be different due to sampling errors. Instead, what we do is we go a level up and say, what about the population means, which we are going to estimate from the sample means. But in our protocol, we say there is no difference between the two population means. And we can say any difference that we observe between the two samples is just can simply be explained by sampling error. It could mean, in this case, that the two populations are in fact one population. There still can be two populations, but we can't discriminate between them. And if we've got the null hypothesis, very often you can think of it as there is no effect of the drug. It doesn't do anything because it's exactly the same as the placebo. And any changes that we see in our samples is just simply due to sampling error. It's not doing anything else. We also then formulate a sort of a statement to be sure about what happens if the null hypothesis is not accepted. And we say we have this alternative hypothesis, and we say there is a difference between the two population means. So it's the negation of the null hypothesis. The differences between the two samples cannot just simply be explained by sampling error. It looks like they are coming from two different populations. Yeah? That means if we go for the alternative hypothesis, we say, yes, there is an effect of the drug compared to the placebo. Note, we just say there is an effect. We do not specify that the drug is better than the placebo or that the drug is worse than the placebo. We leave the options open. We just simply say there is an effect. This would mean we have both options still available because we haven't committed anything. And therefore, this would be a so-called two-tailed test. If we say in our protocol, I want to look at whether the drug actually is better than the placebo, then I commit myself. And I say, if I say the drug is better than the placebo, then I'm just interested in, is it better? I'm not looking at, could it be worse? And because I've committed myself, I only have one option. Is it better or not? And that means it is a one-tailed test. Yeah? And so in a way, you've probably heard about equivalent testing, something like that, or what's the other one? What's the opposite of equivalent testing?
It's not non-equivalent, is it? It's not different to.
Not different, yes. So there is no difference. That would be one way of testing, and the other one, the name eludes me at the moment, is it's not worse than the placebo, for example. There are different stages where you can apply a one-tailed test, but my advice would always...
Superiority.
No,
superiority.
Superiority testing or inferiority testing. Is the drug superior to the placebo or not? That would be a one-tailed test. Yeah, but my advice would always be go for a two-tailed, so you don't have to fuff around with anything, and you just simply say, are they different? So this is the first step in the protocol. The second step is set the significance level alpha, and you can choose whatever significance level you want. We said this significance level alpha indicates the type 1 error, the error that you are willing to accept to make a wrong decision, in that you reject the null hypothesis even if you should not reject it. When you say, basically, I sent somebody to jail, although they are not guilty. That is this type 1 error. And you can set it to whatever number, but typically you would set it to 5%. You formulate the decision rules. And I told you, if P is low, the P-value is lower than alpha. If P is low, H naught must go. You reject the null hypothesis in favor of the alternative hypothesis. So you basically compare the P-value with your type 1 error level. If it is lower, reject the null hypothesis. If P is high, H naught can stay. And you say, yeah, fine, we believe there are potentially two populations, but we can't make any difference. So the drug doesn't have any effect if the p-value is higher. The p-value is really sort of a measure of how surprised should you be when you observe some data, given that the null hypothesis is correct. Now, here is the big issue. We need to find the p-value, the probability. And for that, we need to calculate a test score. Each statistical test has its own calculation, has its own test score, which we then usually would map onto a probability distribution if the null hypothesis was correct. So we would calculate, for example, a t-score or something like that, and say, how likely is it to discover this t-score if the null hypothesis actually was correct? And that gives us this p-value. And I told you the p-value is the probability of observing this calculated test score, or an even more extreme one, given that the null hypothesis is accepted. We get the p-value and we compare the p-value with our significance level, and finally we reject or fail to reject the null hypothesis, say, yes, the drug actually is different from the placebo, or we say, no, we can't see any difference. We don't really know whether it is massively different or not. Yep, and that is basically the procedure. And how do we get this p-value? As I said, or I probably have said that yesterday, nobody in their right mind would always do these calculations for the p-value, or would calculate a t-value, especially not with our data system here, where we already know that it might be a little bit iffy because it breaks the rule of having the same observations. So how do we calculate this p-value? As I said, usually we would use a calculator, but Excel actually also can do that and calculate the t-score, go basically through the entire calculation and come up with a p-value at the end with this probability that we can just simply take. And I'm going to our wonderful calculator that I showed you, and I will later on put up the link to it. So here is, I showed you when you go to this calculator, there is this tab here where it says two sample t-test, because we have two samples with and without drug. All you need to do is really plug in the numbers for sample 1. This is without the drug. Plug in the numbers for sample 2. What what it will show you is the distribution that it thinks the population should look like. So for sample 1, it calculates the mean, 58.175. And this one here, plus minus 23.4, that is the 95% margin of error that we use for the confidence interval. It even shows you the lower and the upper bound of the 95% confidence interval. So this is incredibly useful for the third question of your assessment. Okay, just forget that. Yeah, it does it with the second one as well. So we see the confidence interval for the second one is much smaller. Yeah. So the variability for the second one is much smaller. But what it does is it will give you actually a p-value. P-value equals 0.046 when we do this calculation, when we compare this. So what is your verdict? P-value is 0.046. We set alpha of 5%. Should we reject the null hypothesis or not? If P is low,
it must be rejected.
We should reject the null hypothesis. Yeah, because 0.046 is smaller than 0.05. And we've got a rejection. In this case, rejection is good because it means our decision is there is an effect of the drug. The samples are different from each other, and we cannot explain this difference just simply by sampling error. So the drug most likely has an effect. So 0.046 means there is a difference. Well, the nice thing about this calculator is it even gives you a verdict. Sample 1 is greater, but that's sort of, you should come to that conclusion anyway. So use this calculator because it's extremely useful. Now, I told you earlier the conditions for a t-test, and you can immediately see that at least 2 of these conditions are not met. It's the sample size. The sample sizes are not the same. And the variability of the estimated variabilities of the populations are not the same. So why does the calculator not do something weird? It's for a very simple reason, because what you see here is not the classical t-test. And in fact, I do not think that anyone in their right mind is still using the classical t-test that Gosset has developed over 100 years ago. This is just simply like, using a horse-drawn carriage on the motorway. You don't do that anymore, right? Instead, there is a different test. It is sort of sold as a t-test, but it's actually called a Welch test. And this Welch test is the basis of what this calculator actually does. And also what you can do in Excel, for example. So you can ask Excel to do exactly this calculation. And you can instruct Excel to use this Welch test. I describe a Welch test as sort of a t-test on steroids. Yeah. And the Welch test is more relaxed about sample sizes. It doesn't really matter whether the samples are different in size, and it doesn't matter whether the variances are different. It still assumes that we have continuous data, so you can't use a Welch test with discrete data, and you also need to assume that the populations are normal distributed. But the Welch test makes a few sort of corrections to the original t-test, and that is why we should always use the Welch test. Even if the data have the same sample size, even if the data the populations have the same variances, the Welch test will give the same result as the t-test. But if they are not the same, then the Welch test gives you an accurate measurement, whereas the t-test is just way out, usually. How can you do that in Excel? If you can't do it with the calculator, well, Excel has a nice function in it, and so does Google Sheets. They have exactly the same. The function is, I'll write it down for you. In Excel, you put in equals t.test. And then it asks you for 4 different parameters. It asks you first for the array of your sample 1. So, for example, A1 to A12, that is your sample 1. Then it asks you for the array of the second sample, so say B1 to B15 or something like that. That would be sample 2. That's the data. It then asks you whether you want a 1 or a 2-tailed test. And that's very easy to enter because you will always enter a 2 for a 2-tailed test. And the last one, that's the crucial one. When you perform this Welch test, Excel or Google Sheets expects the number 3. So 2 indicates 2-tailed, and this 3 here indicates that it is a Welch test. Yeah? Shall we have a look if we get the same result? It's the same data, I just copied them. So let's calculate that. So equals t.test. And it wants the first sample. I don't know, what's that? Don't know where this comes from. So it asks for the first number. I messed it up already. So first number. So we take our first sample. Ah, for fuck's sake. It doesn't like me today, huh? T-test. Okay, so that's the first one. The second one. Okay. Now we want 2 for two-tailed, and we want 3 for Welch test. Close the bracket. Keep fingers crossed. Aha. Here we got our p-value. If you remember, it was 0.046, what the calculator gave us. It's the same that Excel or the spreadsheet gives us. Yeah, happy with that? So you can do a t-test. Well, not a t-test, it's a Welch test. But always go for Welch test. Actually, while we are at it, we could also apply the classic standard t-test, where the variances are the same and the sample sizes are the same, and see if we get the same result with the classic t-test. Yes, let's try that. All I need to do for the classic t-test is I need to change the number of the test. We said 3 is the Welch test. The classic t-test is 2. Right? And now, drum roll, do we get the same p-value? We get 0.023. Compare that to 0.046 for the Welch test. It's half. It's just by chance it's half.
Oh,
okay. It has no meaning that it's half. I was when I did that, I thought, oh, why is it half? But it doesn't have any meaning. But you're absolutely right. It's weird, and it's factor 2 out, right? And the reason why it's out is because the conditions of the classic t-test do not apply. That's why we need to do this 3, the Welch test. Yeah, makes sense? Brilliant. Okay, this was the typical 2-sample test. So 2-sample t-test, if you like. Wasn't t-test, it's the Welch test, but nevertheless. So you can do that in the calculator and in Excel, Google Sheets, very easily. We can also, we probably need to say that samples were independent. So it's usually referred to as the 2-sample independent t-test. We can also do something if Clapper harps on about its 2 samples, maybe we can even do a 1-sample test. We just have 1 sample. What do we want to test with that? Well, very simple. Very often you find yourself in a situation where you have some measurements. So you have, say, blood pressure. You measure them, continuous data, and you have a reference value. Yeah, you have a reference value. The reference value should be, let's say, 120. And you want to know whether this 120, the reference here, could be similar to the mean of the blood pressure here, of your samples. So you've got only 1 sample, but you want to know is the sample similar to my reference value? And the way you would formulate that is you would just simply say, the null hypothesis, there is no difference between the population mean of the first, from which the first sample was taken, and the reference value. Any differences that we observe is just simply due to sampling error. You do basically exactly the same, you just marginally change the wording of the null hypothesis. Alternative hypothesis would be there is a difference between the population and the reference value. And in this case, we can't explain it by sampling error only. There is a true difference. You set up your alpha, you make your decision rules. It's terribly boring. It's always the same. And then you calculate a p-value. Unfortunately, neither Excel nor the calculator have a sort of a built-in function to do that, but there's a workaround. You just simply say, actually, my reference value, this is my second sample, if you like, but it's not the sample, it's the whole population. So we can easily add another value because we know it's 120, or we could do another, say 120. What would be the standard deviation of that, of these 3 times 120? All 3 values the same. It would be 0. Absolutely right. So the standard deviation would be 0. Yeah, and that's exactly what we want. So what we do is, let's say we go back to our example previously of the data, and we want to say, let's have a look at this one here. This is tumor size. Let's say we do a reference value this time of 50 and 50 or so. Yeah, we want to compare, is the population mean of the tumors without drug, is it in the range of 50? So what we can do is we do exactly this calculation in our calculator, and what we do is just delete that and enter 50 twice. That's our reference value. And we get a p-value. P-value equals 0.44. What does 0.44 mean if we set alpha to 5%? Shall we reject or not reject the null hypothesis?
Reject. Reject the null hypothesis. Reject it. Reject the null hypothesis.
I give you a chance here.
Oh, no, don't reject it. Exactly.
We failed to reject the null hypothesis. You are absolutely right. Yeah, because it's 0.44, which is larger than 5%. So we failed to reject the null hypothesis. So we say there is no difference between the population mean of the drug, from which we have taken the sample, and the reference value. There's no difference between them.
So the 250s you put in, was that just the reference value?
That is just the reference value that I put in. Yeah. Excel does exactly the same. You can do this Welch test again. again, like I've just done in the calculator with 50 and 50, for example, and the formula for Excel would be exactly the same with the different groups, 2 and 3, and it will give you the same value. Yeah? This would be called, imaginatively, a one sample t-test. Yeah? Happy with that? One sample t-test. Although, technically speaking, it's still a Welch test, but people always call it one sample t-test. We have one more t-test that we could do. And this brings us back to what I told you previously, whether the samples are independent from each other. Because this time we do something crazy. We do something that you will do in a clinical trial routinely. What you usually have in a clinical trial is you don't very often have two totally separate samples that you take. Very often, you measure the same patient twice. So you have patient 1, patient 2, 3, 4, 5, and so on. You say, without the drug, I take the measurements. And then I give the same patient the drug plus drug. So what you basically do is you then take these measurements, and what you have is a sort of, I describe it as a before and after treatment. You measure the same person before and after the treatment. This has massive advantages because you have a sort of an internal standard. You know that the changes that you see are specific to that one person. In this before and after. But the problem is the two samples, without and with drug, are no longer independent. They are depending on the same person. So basically, each person has its own two measurements that you see. Yeah? And that's a very powerful tool, but we cannot use our two sample T or even Welch test because now the samples are no longer independent. They are dependent on each other. Yeah? How can we deal with that? If you sort of think about it, there is a nifty trick that one can apply. What you can actually do is you can say, right, what we do is we calculate the difference for each patient. So let me draw that again. 1, 2, 3, 4. That was minus drug plus drug. And now you calculate the difference between, it's usually plus drug minus drug. And for each patient, you calculate this difference. Just simply by subtracting the minus drug from the plus drug value. Yeah? Something like that. So you've got one column, basically compressed the data from two columns into one column, but that is the difference column. You don't use the original data, you look at the difference between them. And now you say, basically, what this is nothing different to using a one sample t-test, apply a one sample t-test using the difference values not the plus or the minus drug, you use the difference value and compare it to 0. Why 0? Just simply you want to know, is there a difference between them, or is the difference between before and after, is it 0? 0 now is your reference value in this case. Yeah, makes sense? Very clearly, what you need in order to do that is, and you can immediately see whether it is a sort of a before and after, whether it is a dependent t-test, is you need to have the same number of data for the first and the second column. If one data point is missing or so, then it doesn't work because it can't calculate a difference if one of them is missing. So a typical feature of this, what is called a two-sample dependent t-test, and instead of dependent, you sometimes find matched, because you match the two data points to the same person, or you also find it as paired t-test. Let's move that also out of the way. Okay, so we can do that. So we just calculate the difference and do basically a one sample t-test with 0 as the reference. And because it is so common in Excel to do that, this test, it has a built-in function. It is t.test. It asks you again for the sample, let's say A1 to A5, B1 to B5. It has to have the same number because it's before and after. We do a two-tailed test. And in Excel and Google Sheets, it's the number 1 for paired t-test. Yeah? So it's 1. Basically, this formula in Excel is your savior. And all you need to remember is that, as I said, this is the tail. Leave it always at 2. It's a two-tailed test. If it is paired or matched, it's a 1. If it is not paired, it is 3. Do not touch 2. Touch 2 and you get the classic t-test, which is just simply BS. Happy with that? Can you do that? Well, it's fairly straightforward, right? Brilliant. So we have done testing of 2 samples, continuous data. We can do this 2-sample independent t-test if the data are independent, or 2-sample dependent matched or paired t-test when the data are linked to the same sort of entry. Yeah? And we can compare continuous data sample to a reference value. And we got the p-value. Now, the problem with the p-value is that it is a decision tool. It is basically, it tells us, should we reject or not reject the null hypothesis. It is like a pregnancy test. It is, are you pregnant or are you not? We had earlier p-values of 0.046, which is close to this 5%, yeah? So people might intuitively say, oh, well, we are very close to this boundary. So, you know, there is maybe we should, and it gives us a strength of this, how strong the evidence is. No, that's not what the p-value does. It is just simply a cutoff point. You are pregnant. But it doesn't tell you how far into pregnancy you are. It doesn't tell you whether you have twins or whether it's a boy or a girl, or all it tells you is that you can kiss your social life goodbye. You can say goodbye to, you know, lie in on a Sunday or something like that. Life's over. And also, you know, forget your bank account because little monsters will bleed you dry, right? But that is what the p-value does. Doesn't tell you how big this effect is that we observe. Make sense? Wouldn't it be nice, actually, to find a way that gives us this additional information? We see that there is a p-value, we can calculate it, but how big is this effect that the drug actually has? I tell you after the break. Still makes sense? Is it too slow? No? Still makes sense?
Yeah.
Is it too slow?
No, it's good for me. I don't know about everyone else, but
Thank you.
I need to be stopped. I had another Matthews last night. It's too much.
I just keep skipping breakfast.
Sorry for the late. We didn't find parking anywhere. Where we parked for the past 2 days, all full. Anywhere in the sports car park is all full. So
I
we're like driving around.
don't get it. It is holidays. What are you doing? I'm always worried that, I'm too fast, or too slow, or whatever. That's pretty good. Thank you. Right, let's see if there are any new developments. You've seen it?
New developments are.
Good morning.
Morning, everyone.
Yeah. On the university.
I'm very gifts.
Oh, we like gifts. Hoping they're edible gifts.
Fine.
I didn't get a snack today because Esther said she was bringing in.
Oh. Oh. I was actually
Wow,
thinking of
Jesus,
getting
man.
some donuts or so.
Snapchats.
Oh,
And cookies.
homemade.
No. I mean, yes.
Home board.
Yes.
Oh, that's lovely, thank you. Yeah, the new developments at the university. You've heard?
No?
No? Kirsty? You've heard?
What other developments?
Merger
No, don't think so.
has been announced.
Really?
Merger with who?
University of Kent and what is your guess?
Christchurch?
No? Greenwich.
Really?
Yeah.
Oh, wow.
The first big university merger. The new vice chancellor will be the vice chancellor of Greenwich,
Okay.
and it will be a massive change,
Yeah.
basically everything. So EM25 will probably go
Oh.
immediately out
Darn.
the window.
No.
Yep.
When was that? Is that
This morning.
this morning? Yeah.
Apparently the leadership was informed last night.
Are you leadership? Were you informed last night?
No. God, I'm the lowest of the low. The stuff that you trod in.
Oh, I wouldn't have guessed. Yeah. Like in terms of moving forward in competition, it helps, I guess, especially for friendships.
Well, I mean, what I think the spin is that we can make this super university, which apparently the working title is London and the South East University Group, that we are calling ourselves now, with Kent being a sort of a branch. Sounds like everything will be leaner. All the administration will be sort of into one.
Don't talk to me. I'm not listening because I've just gone through a merger with my company.
It's fun, isn't it?
It's the worst thing I've ever done in my life. Worse than selling the company. I thought that was going to be the best thing, but no. Mergers are horrendous.
It's not easy for you anyway, is it? Let alone have that.
Well, we are the junior partner of Greenwich because There are more students,
Okay.
more financial
Mm-hmm.
backing. They
Well,
are
that needs to be
longer.
right. Okay, campus school.
Apparently they keep that.
But Kent's got more,
Does that mean
Kent's
you
a better university, isn't it? In
Sorry?
terms of, Kent's better in terms of academic standing though, isn't it? I don't know about that.
You should.
Yeah, that's what that is, isn't it?
Cool, hey? On that on a Wednesday morning.
Compatible.
I think
Do
we
you want to just take away your more?
we need stronger stuff, right?
Yes, taking this back. You should go get some gin.
No, I was thinking of wheat cookies.
Oh.
So, yeah.
I thought we just did it this year and then.
Always changes, but if you're not changing, you're not moving forward. So, you know.
I just wish they had done the change from the beginning and done it right, so then we wouldn't have had to do once again. No, again. Hindsight's a great thing, isn't it? Okay.
So all the stuff with the, you know, different term, the change in terms,
Yeah.
I don't think that Grant will buy that. So we're going back to whatever they propose.
I wasn't live for fun.
Yeah.
Yeah.
Thank God I'm so old.
Well then, if they're going to do that and streamline staff, they're going to give us more stuff then to be able to do
They give us?
more staff. We can have resource to then get more staff to be able to do that.
I don't know how many of the week this year.
Yeah.
But,
No.
Exactly.
no, it will be less. And there will be whole departments will probably be moved to Greenwich or wherever. They have got several campuses, of course.
Yeah.
So it could very well be that Medway becomes a boost.
Medway will get into it. I don't like a business, so I bet they'll try and get that there. Yeah, but you know.
Cool stuff, eh?
Yeah.
In the morning comes with career progression opportunities though when they're graduates, because if you stay in it and you're decent, there's normally attrition and then rolls around for people that stay. So
When they're recruiting, if you look at their job descriptions and their salaries are better because they're financial. The ones I'm seeing come up and understand the perks and things. So
yeah, they will align them. But
Yeah.
have to.
so you know there will be. I'll probably get a pay rise, but
Be nice.
might be able to get new people in.
No,
It makes a difference though sometimes. You know, people have their jobs. It's it just makes a difference.
Okay, shall we? How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we've got 5 people.
Cookies or flapjack?
Thank you very much. Was the rest still smoking? Aha, good.
Even the other day, no. Yes, life is too short to like. What is there a kidding on this? What have you done?
Not me, not me. That was Kirsty.
My student ID received his pass, so I had to pay for me. Yeah, they dragged me back the ground too, so I didn't.
Okay, have we got everybody back? Brilliant. Don't fall over the cable, please. Okay, so we said basically p-value is just simply the decision tool, but wouldn't it be nice if we could say how big an effect actually is? If the drug has an effect, is it a big effect? Is it sort of, yeah, who cares really in practice? Doesn't really matter. It's a little bit like, you know, you buy a packet of crisps and you do that a lot of times. It's 500 grams in it, say, and then you do the sort of the statistics and you find that it's not 500 grams, it's 10 milligram less. And that's statistically significant, but actually, is it of any importance? 10 milligram, would you even notice 10 milligrams in crisp or not? I had this discussion a couple of years ago with an undergraduate student, and he argued the case, yes, it is absolutely important to have it exactly precise, you know, not any deviation. It needs to be 500 grams, not 499.99 grams. You wouldn't know. So it would be a very small effect. But if it was, say, only 300 grams, and it says 500 grams on the package, you would be pissed off. So in this case, it would be a big difference. And that is actually a very common calculation in statistics. It's called effect size. And the effect size actually tells you how big an effect you actually have. And each measurement in a way, or each test, each data system that you use, data format, has its own effect size. The effect size in our case, where we are looking at continuous data, for continuous data, the most common effect size is called Cohen's d. You heard about Cohen's d? No? Yeah. Cohen's d is a measure how big the effect is when two samples are apparently different from each other. How do you calculate Cohen's d? Cohen's d is fairly straightforward to calculate. You take the difference between the two sample means, and then you divide by sort of a rather unwieldy beast, which is n1 minus 1 times the variance of sample 1 plus n2 minus 1 times S2, the variance, divided by n1 plus n2 minus 2. Looks a little bit horrible, but actually once you've got n, s, and the mean, it's not terribly complicated. But actually to help you with that, on my website, for which you hopefully have the link, there's an effect size calculator on it. So here, common effect sizes, and as I said, Cohen's d is the most, sorry? Yeah. Cohen's d is the most common one for these continuous data. If you've got a small amount of data, you have to add a correction factor, but we don't worry too much about that. So I have put in the number of our test where we said we reject the null hypothesis with drug and without drug. So all you need to do is enter the data into these two boxes and then click Run Bootstrap. And what it does, it will give you a value for Cohen's d. So in this case, it will be 1.2. 1.2? It's just a number, isn't it? What the hell does that mean? Well, there is a sort of a convention. And the convention is here. That's for Cohen's d. If the effect size is smaller than 0.2, forget it. There is no, you don't see anything. If it is between 0.2 and 0.5, it's a small effect. If it is below 0.8, it's a medium effect. And if it is above 0.8, it's large. There is a large effect. Yeah?
Can you go back onto the equation, please?
Yeah, of course. Usually, what we do is just simply calculate the absolute value. We don't care about negatives. Yeah, sorry, I'm in the way. So this is how you calculate Cohen's d. And we got a Cohen's d of 1.2 or something like that when we do this calculation. According to our statement, or according to this table, there is a large difference, a large effect. And it's always good when you report your results, you say, we had a p-value, We had a p-value of 0.046. That means we rejected the null hypothesis. So we said, yes, the drug has an effect. And now I can report Cohen's d, where it has a large effect. And I guess this is what you're looking for when you are doing clinical trials. You don't want to, fuff around with namby-pamby things where you have, it's just squinting a little bit, and with the wind blowing in the right direction, I can see that there might be, I might do something, No, you want power. You want absolutely, this is how we are dealing with that. This is the drug that you want to develop. It has a large effect. When they did the Viagra, there was hard evidence that, what? Let's say something stupid, that there is a massive effect, right? So they probably had effect sizes which were way higher than 1, because otherwise a company would not develop anything that has an effect size of 0.2 or something like that. It's not worth it. Okay, so that is the effect size, and I think tomorrow I will then use this effect size also to show you that we can do something additional, quite useful with this effect size. We can calculate whether our sample size is big enough.
Question, for Cohen's d to calculate it, is there like an Excel formula for it?
No.
Yeah,
Cohen's d, there is no specific function in Excel. You probably have to enter this equation or go to this calculator and use it in the calculator.
Can you go on to the, let's just scroll down a little bit to the significance thing? Yeah, thank you.
Yeah.
Sorry, I didn't quite get that done.
Okay, so this is basically continuous data. But you see, it's a bit boring because we only can, I showed you how we can compare 2 samples. That is why it's called a 2-sample t-test. Bless you. 2 samples that we compare. But what about if you've got more than 2 samples? Let's say you want to compare placebo with drug A and drug B. And you want to know, do these drugs do something? Yeah? Would be cool if we could not just compare 2, but if we could compare 3 or 4 or 5 or 10. Of course, what we could do would be, I'll see if I can find some example. Yeah, beautiful. I've got placebo, drug A, drug B, and we want to compare them. Yeah. Can I have, from what your knowledge is at the moment, can I have creative suggestions how we could compare 3 drugs with each other?
Could you compare the difference between drug A and B with the placebo?
You could do that, yes. That would be a solution, yes. Okay, we've got a drug C then as well. then you are, that doesn't work.
You can compare each drug with the placebo individually.
I love that idea. So basically what you do is you compare the drugs with each other or and the placebo. So you do basically pairwise comparisons. Yeah? So you would compare, oh, let me write that first, comparing several samples. So minus drug A, B.
These have to be independent of one another.
In this case, they are independent from each other.
Do they have to be?
Yes, they must be independent from each other. Because in the first place, we just want to know, is there a difference between the drug? Yeah. So we would do minus drug versus A minus drug versus B minus drug, sorry, that's not minus drug. What would be the last one? That would be A versus B. Yeah, true? So I compare this, I compare this, and I compare this one here. So I do 3 comparisons. Yeah, makes sense? With 3 comparisons, if you do that, that's fairly straightforward. You do basically this t-test ding, ding, ding in Excel 3 times, and you get 3 p-values for it. So we get p-value 1, p-value 2, p-value 3. And you would compare them now to your significance level. Each one compared to alpha, each one, and say, yes, significant difference, or no, not significantly different. And in theory, all is good. But it's actually, if you think about it, with the jury yesterday, we had only one defendant, right, who stole the cookies or not. We had to make a decision. Was she guilty or not? Of course, she was not guilty, but, you know. But now we are sort of in a position where we not only have to make one decision, but we have to make 3 decisions, basically at the same time. So in a way, we probably have 3 defendants, not just one. Yeah? And I, as the judge, have to say, I don't want to make a crucial mistake today. I want to still maintain my error rate of 5%. But if I have a chance of 5% making the wrong decision with one, and then have another error of 5% making the decision with her, and then make another decision with a 5% error rate with you, then obviously the errors will stack up. Actually, they don't add up. It's far worse. They go sort of exponential almost. Yeah. So my chance of making an error that day by just sending one of them down goes up. But I don't want that. I want to still maintain my 5% error rate. And that is why we need to do what is called family-wise error rate correction. Oh, that's a mouthful. It's short FWER correction. We need to make sure that our error does not add up. And there are several methods that you can use for this correction. The most basic one, the easiest, the simplest correction that is sort of available on the market. You don't have to do a lot of calculations, because what you do is you say, okay, instead of alpha that I've set to 5%, I use an individually much smaller error. I just say I allow myself, instead of 5% error each time, I allow myself a much smaller error only. I need to be really sure that you did it before I send you down. Not just 5%, much lower than that, because when I send 3, when I charge 3, then they will all add up again. And I need to make it such that if I sentence all 3 of them, it goes back to 5%. The easiest way is, instead of using alpha of 5%, I use alpha divided by the number of p-values. Because then, when I do that, and I judge every one, they add, or not necessarily add up, but at the end of the day, when I have done all the p-values, I can be sure that overall, I'm still back to my 5% overall error rate. Yeah, makes sense? This method has a name. It's called the Bonferroni correction. Bonferroni correction. And what we are actually correcting, what we are adjusting, is alpha. Adjusting alpha, the significance level. We reduce it, so instead of alpha equals 5%, we use a new alpha, alpha adjusted, of 5% divided by 3 in this case. And that is our new alpha with which we compare the p-values. So if we had, here it would have been, didn't matter. If we had an original p-value of equals 0.046, we would have rejected the null hypothesis because it's smaller than 5%. But now when we have a bunch of p-values, we say we compare to 0.05 compared to alpha adjusted, which is 0.0167 or something like that. Is that right? Probably. And 0.046 is larger than our adjusted alpha. So 0.046 now is larger than 0.0167, and therefore we fail to reject. I need to be far more conservative with my judgment in case of the guilty verdict, because overall I only want 5%, but you know, I've got 3 defendants, and therefore I need to be far more conservative.
What would that tell you?
This tells me now that if I have, for example, placebo versus A, previously I would have said, yes, there is a difference between placebo and the drug. Yeah. Now I do 3 comparisons where I do all 3 of them, and I say, no, I can't reject the null hypothesis. I believe that A, the drug, and the placebo are pretty much the same. Yeah, makes sense?
Yeah.
So that is this family-wise error rate, or error correction, FWER correction, Bonferroni method. As I said, Bonferroni is the easiest one for us, will do. The proper statisticians will not use a Bonferroni method because it is sort of a sledgehammer method. It's really brutal and it is very conservative. That means you probably will not easily see an effect. And there are methods where you not just adjust this significance level that you compare, you can also adjust the p-value, and that is more common. So there is something Holm, Bonferroni, Benjamini, Hochberg method, you name it, it's a lot. But for our purposes, this family-wise error rate correction is absolutely fine. Now, you see, with 3 samples, it's absolutely straightforward to do that because all you need to do is 3 t-tests that you do. Yeah? And that's easy. But when you have more samples that you want to compare, so placebo, A, B, and C, you get more comparisons, right? How many do you have if you've got 4 samples to compare? So, first with the second, first with the third, first with the fourth, second with the third, second with the fourth, third with the fourth. Okay, 4, yeah, we can manage that. That gives us 6 t-tests that we have to do. Yeah? Okay, 6 t-tests. Manageable. can do it. Gets a little bit boring, but we have to adjust them. We divide alpha now by 6 because that's the 6 p-values that we get. Can do that. 10 samples. First with the second, first with the third, you get the gist, right? You can actually calculate how many samples or how many tests you need. The equation for that is n times n minus 1 divided by 2, whereby n, the number of samples is. So you've got 10 for 10 samples. It's 10 times 9 divided by 2. That is, you need to do 45 t-tests. You probably, by t-test number 30, you lose the will to live. By t-test number 40, you are considering sticking a rusty nail through your eye socket. And by 45, you say, hallelujah, and then you discover that you did a wrong calculation, but you don't know where, and you just simply then go to the pub and say, my life is not worth living. That's what I do. Wouldn't it be nice? And what could easily happen is that because we are now so low in the comparison, because we have to divide alpha by 45, that we will not find a p-value that is below this very low alpha now. It could very well be the case that we come to the conclusion, actually, in none of the 45 cases, we reject the null hypothesis because the p-value is always higher than alpha. And you think, for flip's sake, all this time, 45 t-tests, you go gaga, 45 t-tests for what? Nothing. No effect of any of them. You can trust the method, but no. Spend a lot of time, just go crazy. Wouldn't it be nice if we had a method that tells us, actually, they are all exactly, the means are all the same, so that we just simply can do that straight from the start. We do this method, and we test, is any one of these, say, 45 comparisons, is there one, at least one of them, that we need to look closer at? Or do they all say these 10 samples, basically there is no difference between the means? That would be cool if we could do that. That could save us so much time. And luckily, there is a method. I get rid of that. I don't need that, actually. There is a method. You probably have heard about this method. This method is called a one-factor analysis of variance. We are looking just at one factor, drug or whatever this is, at different levels. And our null hypothesis for this is there is no difference between the population means from which the samples are taken. Any difference that we see is due just simply to, or can be explained by sampling error. It's exactly the same that we had before, but now we do that for more than just 2. And mathematically, this would be written like that. All the population means are the same. That's our null hypothesis. Yeah. The alternative hypothesis would be at least one population mean is different. At least one of them. Could be 2, could be 3, could be 4. Yeah? That they are different. So we are basically testing with this method, are they all the same? Because if they are all the same, then I don't have to do this family-wise testing, because I know they are all the same. Job done. I can still go to the pub. But if I have to reject the null hypothesis, then I have to say, damn it, there is at least one of them, and now I have to find out which one it is. So that is the one-factor analysis of variance, and because statisticians like things to be short, this is abbreviated. Does anyone know? This is called an ANOVA, an ANOVA, which stands for analysis of variance. And what it basically does is it tests the null hypothesis. Are they all the same? The output of an ANOVA is again a p-value. We can set, for example, like we did previously, we set our significance level alpha. We set that to 0.05 or 5%. We don't have to do any adjustments at that point. We just simply test the hypothesis. They are all the same. 5%. We say if p is low, h naught must go. If p is high, h naught can stay. We reject or fail to reject the null hypothesis. How do we calculate the p-value in this case? Well, luckily, Excel has a function for that, where you can do that, but you have to use the data tab. Excel Sheets struggles a little bit with an ANOVA, but there are some add-ins. And what the ANOVA tells you is, yes, they are all the same, or no, they are not. If they are all the same, job is done. We don't have to worry. We know that they are all the same. If the ANOVA tells you, no, at least one of them is different, then the hard work starts. Because then you have to do all the 45 tests. That's why these tests are called, that's why you only do these tests once you have done the ANOVA. The ANOVA saves you a lot of time if you've got many samples to compare. If you've got only 3 or 4 samples to compare, then it's probably not worth running an ANOVA, because you're probably faster doing the t-tests, the 3 or 6 t-tests, straight away, instead of doing the ANOVA, because you probably have to do them anyway. So my advice would be, if you have 3 or 4 samples to compare, do these tests straight away. Don't bother with an ANOVA. Only if you've got more than 5 to compare, then you run the ANOVA, and I will put up on the website a YouTube video that shows you how you can do an ANOVA in Excel, if you really must. The big disadvantage of the ANOVA is it does not tell you which one is different. And that's why you have to do these additional tests after the ANOVA. That's why they're called post hoc tests. And that is with a C, it's not a hog. Post hoc tests. There are a number of tests that you can do. One of them is two-key. It's not the turkey, it's the same guy. That is a two-key post hoc test. It's not as powerful as these individual t-tests with the family-wise error correction. So I would, and Excel has absolutely no idea how to do a two-key test, but it can do the t-tests very easily. So a lot of people say, oh yes, you need to do an ANOVA and the two-key tests. Once the ANOVA shows you a result, just, if you've got 3 or 4 samples, just do the comparison with the t-test and the family-wise error rate. You need to do that. But don't bother with the ANOVA, only if you've got more than 5. Then do the ANOVA first. And if there is a problem, if the ANOVA says, yes, there's a difference, then you have to do the individual t-tests. You had a question?
No, I don't.
No.
Sorry, what's the two-key test for then?
The two-key test is basically doing exactly the same as the t-tests. It says, watch out, sample 18 and sample 133 are different from each other. But again, you have to run a lot of two-key tests for that. Or you use R that has a built-in two-key test. But it also has a built-in family-wise error rate correction for multiple t-tests. So I would stay clear of two-key tests. But I know that the, bless you, the sort of the hardcore clinical trial people love two-key tests for a reason that I have not yet found out why this is the case. So I would always go for Welch tests, pairwise comparison with the family-wise error rate. Are you happy with that? Whoa, that was a lot. Do you think we deserve a break? Shall we have lunch? Yes, lunch break. Back at 2? Is that right?
Well, we've got another session, it's 12:45.
Okay, I will be back at 2. Any questions? Fantastic. Thank you very much. See you later.